This lecture is on fluid statics. Let's review the definition of pressure. Pressure is the force acting normal to an area divided by the area. So, as a formula, P, which is pressure, equals delta F divided by delta A, which is force divided by area. And this figure is showing a very small portion of a whole surface, and we can consider that to be a point, and because of that we can write it as P equals dF divided by dA, where this area here is very close to 0. And if the surface has a finite area and the pressure is uniformly distributed over the area, then the average pressure, which we can show by P sub AVG, or average pressure, equals F divided by A. And pressure can have the units of pascals in SI units, which is newtons divided by meters squared. Next, let's see what's Pascal's law. So in the 17th century, the French mathematician Blaise Pascal showed that the intensity of the pressure acting at a point in a fluid is the same in all directions. So this figure is showing that, for example, if this is a bowl that is filled with water, if you apply pressure to it, then the fluid inside will exert forces on the inner kind of surface of this ball in all directions, and all of those are the same. So these are equal force in all directions. Let's have an example that we use the Pascal's law. So the question is, a pneumatic jack is used in a service station. If the car and lift weigh 25 kilonewtons, so the weight of the car and the lift together is 25 kilonewton, determine the force that must be developed by the air compressor at B to raise the lift at a constant velocity. Air is in the line from B to A, so in this line from B to A, we have air. The air line at B has an inner diameter of 15 millimeters, so inner diameter of this line, this air line, is 15 millimeter, and the post at A has a diameter of 280 millimeters. So the diameter of this post is 280. Okay, let's see how we can solve this question. So due to equilibrium, the force created by air pressure at A is equal and opposite to the weight of the car and lift. So we have two pressures here, pressure created by air and then pressure due to the weight of this car and this post, and they have to be equal. If we analyze this portion of this system, PA, pressure at A, equals FA divided by AA, in which F is the force and A is the area. So if we plug in the numbers, the question told us that the force is 25 kilonewtons, which is the weight of the car and the post. And then in the numerator, we have the area of this post, which is pi r squared. We know that the diameter is 280. Therefore, r, which is the radius, is half of it, 140 millimeters. And if we convert to meters, it is 0.140. So the result would be 406 times 10 to the third Pascal. So this is pressure at A. Next, the pressure at each point is the same in all directions. So this is Pascal's law. Therefore, the same pressure is transmitted to B. Same pressure here will be transmitted to B. So in order to find FB, we have to use this formula that PB equals FB divided by AB. And as I said earlier, since pressure here is equal to pressure here, then the number that we found here as PA, we can use it as PB. So 406 times 10 to the third newtons divided by meters squared equals FB, which is what we want to find, divided by the area of this airline, which is pi r squared. We have the diameter divided by 2, converted to meters, and we find the area here. So if we solve this fraction, we get FB equals 71.7 newtons. All right, next topic is on absolute and gauge pressure. So pressure in the vacuum space is zero absolute pressure. And any pressure that is measured above this value is referred to as absolute pressure. Or we can show it as P sub ABS, which is pressure absolute. For example, standard atmospheric pressure is the absolute pressure that is measured at sea level and at a temperature of 15 degrees C. So P atmosphere is 101.3 kilopascals. And this is an absolute pressure. Any pressure measured above or below atmospheric pressure is called gauge pressure. And we can show it by P sub G, which is gauge pressure. Because gauges are often used to measure pressure relative to the atmospheric pressure. So we can have this formula based on these definitions. P absolute equals P atmosphere plus P gauge. Therefore, P absolute is always positive because it's relative to perfect vacuum, so it's always positive. P atmosphere is also always positive, but P gauge can be negative because it's relative to the atmospheric pressure. And again, any pressure measured above or below atmospheric pressure is called gauge pressure. So it can be positive or negative. Example, the air pressure within the bicycle tire is determined from a gauge to be 70 kilopascals. If the local atmospheric pressure is 104 kilopascals, determine the absolute pressure in the tire. Solution: before the tire was filled with air, the pressure within it was atmospheric, which was 104 kilopascals. And if we use the formula P absolute equals P atmosphere plus P gauge, then we find P absolute equals 104, which is the atmospheric pressure, plus the gauge pressure that was 70 kilopascals, and the answer is 174 kilopascals. Pressure variation for incompressible fluids. Okay, when the pressure at the surface is the atmospheric pressure, or P0 equals P atmosphere at the surface, then the term gamma H represents the gauge pressure in the liquid. So the gauge pressure inside the liquid at any point equals gamma H, in which gamma is the specific weight and H is basically the distance from the surface of the water to the depth that we are studying. If we rearrange the formula in the last slide, we get H equals P divided by gamma. And in this case, H is called pressure head. And it basically indicates the height of a column of liquid that produces the gauge pressure P. As an example, if the gauge pressure is 50 kilopascals, Then the pressure heads for water, in which gamma W is 9.81 kilonewtons divided by meter cubed, and mercury, in which gamma Hg equals 133 kilonewtons per meter cubed. See the difference? Or HW, which is head of water, and HG, which is the head of mercury, are the following. The height of water that produces the same pressure is 5.10 meters, whereas the height of mercury that produces the same pressure of 50 kilopascals is only 0.376 meters. And this picture is showing that. Another example, the tank and drain pipe in the figure are filled with gasoline and glycerin to the depths shown. So depth of gasoline is 1 meter and depth of glycerin is 1.5 meters. The question is determine the pressure on the drain plug at C. So we are going to find the pressure at this point. Report the answer as a pressure head in meters of water. And take rho of gasoline as 726 kilograms per meter cubed and rho of glycerin as 1260 kilograms per meter cubed. Solution, the gauge pressure at C is P sub C, which is pressure at C, equals gamma H plus gamma H. But the first term here is for gasoline, and it goes from point A to B times HAB. So again, PC equals gamma of gasoline times H of gasoline from here to here plus gamma of glycerin, which is the specific weight of it, times HBC, which is from here to here. So we already know the values for density. So if we multiply density, which is rho, by G, we get gamma. Rho G times HAB, which is 1 meter, plus rho of glycerin, which is 1260 times G. So these two values multiplied is gamma. Gamma equals rho G. So times the height, which is HBC from here to here. The answer is 25.66 kilopascals. So pressure at C equals 25.66 kilopascals. Okay. The pressure head in meters of water at sea equals, based on that formula from last slide, H equals P at C divided by gamma of W, in which we know that gamma of W is rho of W times G, which is 1000 kilograms per meter cubed. So this is density of water times gravity, which is 9.81 meters per second squared. So gamma of water is 9.81 times 10 to the third newtons per meter cubed. So if we plug in numbers here, we already found PC. So we put it here and then gamma of water here. So we get H equals 2.62 meters. And that is the pressure in terms of water head. Measurement of static pressure. In order to measure static pressure, several kind of tools can be used, in which one of them is called barometer. And it measures the atmospheric pressure. So the way that it works, first, a glass tube like this one in the figure is filled with mercury, and then it is submerged in a dish that has mercury inside, and then it is turned upside down like this. So as a result, uh, a space here that can be considered as vacuum forms. So if we analyze the pressure inside this tube, P at B, which is pressure at point B, is equal to pressure caused by this column of mercury plus the pressure above it, in which we can consider as zero, because for moderate temperatures, the vapor pressure created here is practically zero. So we can write PB equals gamma Hg times H, which is a specific weight of mercury, which is Hg, times H, which gives us pressure created by this column of mercury here in this glass tube, plus whatever pressure that exists here, and it is basically zero. Pressure at B is equal to pressure at point C, which is open to the atmosphere. So we can write PB equals PA plus gamma Hg times H as P atmosphere equals zero, because here we said pressure is very close to zero, plus gamma Hg times H, which is equal to gamma Hg times H. So in a static fluid, the pressure at points on the same horizontal level in the same continuous liquid must be equal. So that's the reason that we can say P at point B equals to P at point C. Again, in a static fluid, the pressure at points on the same horizontal level, such as here, in the same continuous liquid, because the liquid is not changing, so we're talking about the same liquid, must be equal. So PB equals PC. So PB equals P atmosphere because it's open to the atmosphere. And then we have this analysis here. For example, standard atmospheric pressure 101.3 kilopascal will cause the mercury column that has a specific weight of 133 kilonewtons per meter cube to rise about 760 millimeters in the tube. So as a result of the atmospheric pressure, the mercury will rise for about 760 millimeters in this tube. Another tool that is used for measuring static pressure is called manometer. Manometers are pressure measuring devices based on the use of liquid columns in vertical or inclined tubes. There are three common types of manometers. First one is called a piezometer tube, which is the simplest type. Next, we have the U-tube manometer, and then inclined tube manometer. This figure shows a piezometer tube, which is the simplest kind of manometers, and it consists of a vertical tube open at the end and attached to a container. The container is attached to a point whose pressure is going to be measured, such as point A in this case. So we can write that PA, which is pressure at this point, minus gamma H equals zero. The reason is that in the previous slide, we mentioned that on the same line, the pressure does not change. So P at this point equals P at this point. Pressure at this point equals pressure at this point. So if we go up from this point, what happens to pressure? It decreases, right? Because pressure increases as depth increases. So if we go up from here to the surface, pressure decreases. That's why we have this negative sign. So PA, which is pressure at this point, equal to pressure at this point, minus gamma H, which is pressure produced by this column of water or liquid, equals zero, because it's open to the atmosphere. And what we have here is gauge pressure. Therefore, PA, which is pressure at this point, equals basically gamma H. So this is regardless of where A is on this line. On this line, pressure is the same. U-tube manometers consist of a vertical tube open at the end, attached to a container, and formed into the shape of a U-tube. The fluid in the manometer, gamma 2, which is this one, is called the gauge fluid. So let's analyze the pressure at point A. So since A and this point are on the same line, we can move from here to here. So PA equals P at this point, PA plus gamma 1 H1. We are going down, depth increases, so pressure increases. And specific weight of the liquid here is gamma 1. PA plus gamma 1 H1, we can go straight to the right because they're on the same line. We don't need to go down and then right and up. We can go straight to the right side because pressure here and here are the same. And then from here, we can go up. So it will be minus gamma 2 H2 equals 0 because then it's open to the atmosphere. So if you rearrange this, we get PA equals gamma 2 H2 minus gamma 1 H1. Another type of manometers is differential U-tube manometer. And it measures the difference in pressure between 2 points. And as you can see, one side is not open to the atmosphere in this case. So consider a manometer connected between containers A and B. So let's write the formula, the equation for pressure again. So pressure at point A equals pressure at this point, PA plus gamma 1 H1 because we are going down, so pressure increases. And then from here, we can go to the right directly, and then we should go up. So since we're going up, then pressure decreases. We can write minus gamma 2 H2. And then from this point to this point, because the fluid changes, we have gamma 3. So here we had gamma 1, gamma 2, and then gamma 3. Minus gamma 3 H3 because we are going from here to here equals PB because they are on the same line. So if we rearrange that, we want to find the pressure difference between A and B. So PA minus PB equals gamma 2 H2 plus gamma 3 H3 minus gamma 1 H1. Another type of manometers is inclined tube manometer. So as you can see, the tube is angled and we have some angle here, theta. So this type of manometer is used to measure small pressure changes, so it's more accurate. So we can write PA, which is pressure at this point, equal to pressure at this point, plus gamma 1 H1 because we're going down, so pressure increases. We can go straight here because they're on the same line. And then from here to here, we're going up, so pressure decreases. But in order to get the vertical distance, we have to multiply by sine theta. So it becomes minus gamma 2 L2 times sine theta. So L2 times sine theta gives us this vertical distance. Because what matters in fluids is only vertical distance in terms of pressure change. So if you multiply L2 by sine theta, you get this vertical distance. And then from here to here, again, what matters is only this vertical distance, which is gamma 3 times H3. And pressure at here equals PB. So if you rearrange that, again, we want to find the pressure difference between A and B. PA minus PB equals gamma 2 L2 sine theta plus gamma 3 H3 minus gamma 1 H1. Let's watch a video.
In this video, we're going to introduce you to the manometer, which is one of the oldest pressure measurement devices still in use today. A manometer is one of the most accurate devices for measuring pressure in the lower ranges. Since manometers are so accurate, they are often used as calibration standards. Some typical industrial manometer applications include fluid flow measurements, HVAC systems maintenance, residential or commercial furnace gas valve pressure measurement. All right, let's get started. All manometers operate on the principle that changes in pressure will cause a liquid to rise or fall in a tube. There are several different types of manometers, and we will discuss many in this video. As mentioned earlier, all manometers operate on the principle that changes in pressure will cause a liquid to rise or fall in a tube. Let's look at a U-tube manometer, as it is probably the most common manometer in use today. We'll discuss how it is used to measure pressure. As we said earlier, a manometer is filled with a liquid. Typical manometer liquids are mercury, water, and light oils. It's worth saying here that mercury was a common manometer fluid in the past, but has largely been replaced due to its environmental and health hazards. Quite often, the liquid is colored to help detect the fluid movement. The tube is filled until both sides are approximately half full. When the pressures are equal, the column of liquid on each side will be at the same height. This is usually marked as 0 on a scale. With both sides of the manometer open to the atmosphere, the fluid level on one side will be the same as the level on the other side, because P1 equals P2. Okay, now suppose one end of the U-tube manometer is connected to an unknown pressure P1, whose value must be determined. The other end is left exposed to the atmospheric pressure, P2. The difference in the height of the liquid on the two sides of the tube is the differential pressure. In this case, the manometer provides a gauge pressure measurement because it is referenced to the atmosphere. Okay, so the total difference in liquid height is 4 units. And this is where the pressure measurement becomes interesting. What does the 4-unit difference represent? Let's assume our U-tube manometer is filled with water. That means that our pressure differential is 4 inches of water column. From our previous videos, you know that inches of water column is a unit of pressure measurement. Using conversion charts, we could easily convert 4 inches of water column to 0.144 psi gauge pressure. As you can appreciate, a U-tube manometer filled with water is only capable of measuring very small pressures. To illustrate, let's apply a pressure of 5 psi to the P1 side of the U-tube manometer. Oops, we don't want that to happen. What if we wanted to accurately measure very low pressure values? If we replace the water with a Merriam red oil fluid, we will get a greater difference in liquid levels. Why is that? Water has a specific gravity or relative density of 1, while Merriam fluid is an oil and has a specific gravity of 0.83. We will get a much larger difference in liquid level with Merriam fluid, resulting in more accurate pressure measurement. In some cases, vendors will provide a U-tube manometer scaled directly in pressure units, such as kilopascals. Manometer users must be aware of meniscus error. Meniscus occurs when the particles of the liquid stick to the sides of the glass tube. Depending on the direction of pressure applied, the meniscus can be concave or convex. Either way, a reading error may occur. Let's have a look at a couple of other types of manometers. One common type of manometer is a barometer, used to predict weather conditions by measuring atmospheric pressure. A barometer consists of a glass tube with one end sealed. An evacuated tube has its open end submerged in an open container of mercury. The pressure exerted by the column of mercury is balanced by the pressure of the atmosphere. The glass tube is calibrated in pressure units. Any liquid could be used in a barometer, but mercury is used because of its high specific gravity. A mercury barometer needs to be at least 30 inches tall. A water filled barometer would have to be more than 33 feet high. A manometer that provides even better accuracy than the YouTube manometer is the inclined manometer. This manometer has a well that contains the liquid and a transparent column. The column is mounted at an angle. The pressure is indicated by the vertical amount the liquid rises or falls in the column. Because of the incline, a small change in pressure will cause greater movement of the liquid in the column.
Another example on measurement of static pressure. Example, the nozzle located in the pipe creates a pressure drop which can be measured with a differential U-tube manometer. A. Determine an equation for the pressure drop, and B. For gamma 1 equals 9.8 kilonewtons per meter cubed and gamma 2 equals 15.6 kilonewtons per meter cubed, and H1, which is this value, equals 1 meter, and H2, which is this value, equals 0.5 meter. What is the value of PA minus PB, which is basically pressure difference between this point and this point? So we start from point A. PA minus gamma 1 H1, because we're going up, and then we can go to the right, and also from this point we can go to the right because we are still on the same line. And then from here we can go up, therefore it's negative minus gamma 2 H2. And then from here, if we go to the right and go down, we get to point B, but for here we have plus gamma 1 times H1 plus H2, because this height is H1 plus H2 equals PB. Therefore, if we rearrange this equation here, PA minus PB equals H2 times gamma 2 minus gamma 1. If we plug in numbers that were already given to us, we get the pressure difference is equal to 2.9 kilopascals. Next example. The funnel is filled with oil and water to the levels shown, while portion CD of the tube contains mercury. Determine the distance h. The mercury level is from the top of the oil surface. So we are going to find h. Take density of oil, or rho sub O, equals 880 kilograms per meter cubed. Rho sub W, which is density of water, equals 1000 kilograms per meter cubed. And rho Hg, which is density of mercury, equals 13,550 kilograms per meter cubed. All right, noting that the gauge pressure at A and D are both zero because both of them are open to the atmosphere, we have 0 plus rho O GHAB. So we start from here. Rho GH is the pressure of this column of oil here. Rho times G times HAB plus rho W GHBC, which is pressure caused by this column of water here, minus rho Hg, which is density of mercury from here to here, GHCD. HCD is from here to here, equals 0. So we started from here and finished here. If we plug in the numbers that were already given in the question, we find H equals 0.651 meters. Another example, determine the difference in pressure between the center line points A and B in the two pipelines if the manometer liquid CD is at the level shown. The density of the liquid in AC and dB is rho equals 800 kilograms per meter cubed, and in CD, rho CD equals 1100 kilograms per meter cubed. Starting at point B and moving through the manometer to point A. So we can start from B and then go this way. PB minus rho GH BD, which is from here to here, we are going up, so it's negative. PB minus rho GH BD. We can go from here to here, plus rho CD times G times H DC, which is from here to here. So from this point, we can go here, and then from here, we have plus rho G HCA, which is basically this difference, equals PA. So by plugging in the numbers, we get delta P equals PA minus PB equals negative 1.03 kilopascals. Since the result is a negative number, the pressure at A is less than that at B. Last example on measurement of static pressure. So as you know, the inclined tube manometer is used to measure small pressure changes. So this question is, determine the difference in pressure between points A and E if the manometer liquid, mercury, is at the level shown. The pipe at A contains water up to this point, and the one at E contains natural gas. So we have water here, natural gas here, and mercury here. And for mercury, rho Hg equals 13,550 kilograms per meter cubed. So let's see how we can find delta P, which is the pressure difference between this point and this point. So pressure at E is essentially the same as that at D. Why? The reason is that it's a gas. So applying the manometer rule from point A to point D, from here to here, we have PA, you start from here, plus gamma W times HAB, so pressure caused by this column of water here, and it's positive because we're going down, so pressure increases, plus gamma Hg times HBC. So from here to here, pressure caused by mercury, minus gamma Hg times HCD. So CD is from here to here, and as I mentioned earlier, what matters is the vertical distance. So what you have to do is to multiply this number, which is the length of the tube, by sine 20 degrees. So by doing that, you get the vertical distance. So it's negative because we are going up, pressure decreases. So that equals P at point D, which is also equal to P at point E. So if we just plug in the numbers, we get PA minus PE, which is the pressure difference, equals 14.6 kilopascals. Next topic is on buoyancy. The Greek scientist Archimedes discovered the principle of buoyancy, and it states that when a body is placed in a static fluid, such as water in this case, it is buoyed up by a force that is equal to the weight of the fluid displaced by the body. So in this case, a ship on water displaces some amount of water, So this buoyancy force here is exactly equal to the weight of the amount of water displaced by the ship. Buoyancy arises from the facts that fluid pressure increases with depth, and the increased pressure is exerted in all directions, which is Pascal's law. Therefore, there is an unbalanced upward force on the bottom of a submerged object. So let's look at an example here. So the water ball at left is supported by a difference in pressure. So as you can see, the pressure increases as depth increases. The solid object on the right experiences exactly the same pressure environment. So the buoyant force on the solid object is equal to the weight of the water displaced by that solid object. And that is called Archimedes' principle. And the formula for that, F sub B equals gamma times V, in which gamma is the specific weight of water and V is the amount of water displaced, and F sub B is the buoyant force. The buoyant force F sub B acts through the center of buoyancy, which is C sub B, and that is located at the centroid of the volume of liquid displaced by a body. So, this is an example. The density of ice is about 9/10 that of seawater. Therefore, 90% of an iceberg is submerged, while only 10% remains above the surface. And if the density of the liquid is constant, then F sub B, which is the buoyant force, will remain constant, regardless of how deep the body is placed within the fluid. Let's look at an example here. Suppose there were equal-sized balls of cork, aluminum, and lead, in which the volume of each of them is 10 centimeters cubed, and a specific gravity of cork is 0.2, specific gravity of aluminum is 2.7, and specific gravity of lead is 11.3. Therefore, their masses will be 227 and 113 grams. And each would displace 10 grams of water because their volume is 10 centimeters cubed, and each centimeter cubed weighs 1 gram. Therefore, it yields apparent masses of -8, 17, and 103 grams respectively. So because they displace 10 grams of water, what we have to do is subtract that number from their mass. Because the buoyant force is upward and the weight, which is also a force, is downward. So if we subtract, we get their apparent masses in water. So for the cork, it is -8. For the aluminum, it is 17. And for lead, it is 103 grams. Question here, what happens when they are released from rest in water? The cork would pop out of the water because its apparent mass is negative. The aluminum would sink, and the lead would sink more rapidly. But the buoyant force on each is the same because of the identical pressure environments and equal water displacements. And same arguments can also be applied to a floating body. So previous cases, we had completely submerged bodies, but here we have a floating body. So the displaced amount of fluid is within the region ABCA, ABCA, so W equals F sub B. W is the weight of fluid within the displaced volume. That equals the buoyant force. So weight is downward, it's a vector, it's a force, and buoyant force is upward. So they balance, and this object can basically float on water. And the center of buoyancy, CB, is at its centroid. This principle is useful for determining the volume and therefore the density of irregularly shaped objects. But how? First, we have to measure the object's mass in air. Second, we have to measure its effective mass when submerged in water. Next step, the difference between the real and effective mass gives the mass of water displaced. And next step, we can calculate the volume of the irregularly shaped object. Number 5, we can calculate the density of the irregularly shaped object because we have its mass and also its volume. And that's similar to the king's crown in the Archimedes story. So if you don't know about this story, that what happened, I recommend that you do some research about it. It's very interesting. Next, let's watch a video.
When first studying physics many years ago, our instructor posed this question. A rectangular barge, 300 centimeters long and 200 centimeters wide, floats at the edge of a freshwater lake. A horse jumps into the barge, and the barge sinks 12 centimeters. How much does the horse weigh? Solving this problem makes use of knowledge created by the Greeks over 2,000 years ago. Archimedes' principle. Archimedes investigated density and buoyancy. His millennia-old discoveries are still used today by marine engineers and ship designers, and we will use it to solve the horse problem. Before we start, a quick comment on units. In science and engineering, the terms mass and weight mean different things. Mass is an intrinsic property of matter, and weight is the force of gravity acting on an object. But the term weight is commonly used to describe mass. We say, for instance, that an apple weighs 500 grams, even though grams are units of mass. I will be using grams in this basic investigation, recognizing that a rigorous procedure would require units of force. If you have viewed our video on buoyant force, you will know that objects sink or float based on their density relative to the density of the fluid they are immersed in. This wood block is less dense than water, so it floats. Or at least it floats partially submerged. The submerged portion of this wood block has displaced some water, pushed it out of the way. Let's investigate this displaced water. To collect the displaced water, I have created this overflow apparatus, a tub with a spout. Filling the tub over the spout, we will let water run out until it stops. The surface of the water is now level with the overflow spout. Before we start, let's weigh this wood block. It has a mass of 266 grams. Our overflow tub is ready for use. We have an empty cup on a scale positioned to catch and weigh the displaced water. The weight of the cup has been subtracted. When we lower our block into the water, displaced liquid starts flowing out the overflow tube. The scale is weighing this displaced liquid. After a few minutes, the flow slows and eventually stops. The scale indicates that the displaced liquid weighs 266 grams. Do you remember the weight of the wood block? It was also 266 grams. The floating wood block and the displaced liquid weigh the same, 266 grams. This is not a coincidence. This is Archimedes' principle. The weight of the displaced liquid equals the weight of the floating object. Or, more precisely, the buoyant force acting on a submerged or floating object is equal to the weight of the displaced fluid. Our floating wooden block weighs 266 grams. The water displaced by the floating block also weighs 266 grams. We know that the floating wood block displaces its own weight in water. What happens if I add a weight to this floating block? Like this 126 gram stone. The wood block sinks further, displacing more water. Can you predict the weight of the water displaced by the stone? Did you get 126 grams? That's right. The additional weight of the stone caused the block to sink further, displacing a weight of water equal to the weight of the stone, 126 grams. Now to solve the horse problem. We have a rectangular barge measuring 300 centimeters by 200 centimeters, sitting in a freshwater lake. A horse jumps onto the barge, causing the barge to sink 12 centimeters. How much does the horse weigh? Like the stone sitting on the wood block, the horse has displaced water equal to its own weight. We need to calculate the weight of this displaced water. If you think you know how to do this, pause the video and do the math. The barge, before the horse is loaded, is sitting at this level. It has displaced water equal to its own weight. When the horse jumps aboard, the barge sinks another 12 centimeters. The volume of water displaced by the weight of the horse is a rectangular prism. 300 centimeters by 200 centimeters by 12 centimeters. The volume of a rectangular prism is length times width times height. That's 300 centimeters times 200 centimeters times 12 centimeters. This equals 720,000 cubic centimeters. This is the volume of the displaced water. Now we need to calculate its weight. Fresh water has a density of 1 gram per cubic centimeter. This means that 720,000 cubic centimeters of water weighs 720,000 grams. Let's change this to kilograms. 1 kilogram is 1,000 grams. This means the displaced water weighs 720 kilograms. The horse weighs 720 kilograms, the weight of the water it displaced. Archimedes' ancient principle is still used to determine how far a ship will sink when loaded with cargo. The math involved in this calculation is very similar to the math we use to determine the weight of the horse. This millennia-old principle describes the forces affecting everything from hot air balloons to cruise ships. More science and technology projects and videos can be found at our website, hylaroad.com. Follow the projects link.